After 46 years of exploration, Voyager 1 has finally broken through the ultimate barrier, the heliosphere, and entered true interstellar space. But, the data streaming back from 15 billion miles away is completely rewriting everything scientists thought they knew about the void between stars. This isn't the empty darkness we expected. The space beyond our solar system's protective bubble is alive with invisible forces, mysterious structures, and phenomena that challenge our understanding of the galaxy itself. Today, we're exploring 10 groundbreaking discoveries that prove interstellar space is nothing like we imagined. The magnetic field mystery. The first shock hit scientists when Voyager 1's magnetometer detected something completely unexpected in 2012. Instead of finding chaotic, randomly oriented magnetic fields, the spacecraft discovered that interstellar space has a surprisingly organized magnetic structure. Dr. Leonard Berlanga, from NASA's Goddard Space Flight Center, was among the first to analyze these readings, revealing that the interstellar magnetic field runs nearly perpendicular to our solar system's magnetic field. This sharp 90-degree misalignment suggests we're encountering the edge of a massive galactic magnetic domain. The implications are staggering. These aren't local phenomena but galaxy-wide structures that could influence star formation, cosmic ray propagation, and even the evolution of planetary systems. The magnetic field strength measured at 0.4 nanotesla is actually stronger than predicted, indicating that interstellar space contains more organized energy than our models suggested. This discovery fundamentally changes how we understand magnetic field interactions on galactic scales. The cosmic ray bombardment. Crossing the heliopause in August 2012, Voyager 1 immediately encountered a radiation environment that defied all expectations. Dr. Edward Stone, the mission's project scientist since 1977, watched in amazement as cosmic ray levels spiked by 300% almost instantly. These high-energy particles, accelerated by distant supernova and black holes, bombard everything in interstellar space at intensities that would be lethal to unprotected astronauts. The cosmic ray subsystem aboard Voyager detected particles with energies exceeding 100 million electron volts, radiation levels so intense they would fry electronic equipment within months. But here's the most surprising part. The cosmic ray patterns aren't random. Voyager's instruments have measured systematic variations that suggest interstellar space has natural radiation corridors and safe zones. These findings prove our sun's heliosphere acts as a far more effective cosmic ray shield than anyone realized, protecting Earth and our entire solar system from this invisible galactic storm. The plasma wave discovery. Silence doesn't exist in interstellar space. Voyager 1's plasma wave subsystem, designed by Dr. Donald Gurnett at the University of Iowa, has been detecting constant low-frequency oscillations since entering the interstellar medium. These aren't random static, they're organized plasma waves that create what scientists now call the interstellar hum. Operating at frequencies between 2 and 3 kilohertz, these waves indicate that interstellar space is filled with electrically charged particles constantly in motion. Dr. Stella Ocker, a Cornell University researcher, recently analyzed 5 years of this data and discovered that these plasma oscillations change frequency as Voyager moves through different regions. The waves intensify near density boundaries and quiet down in more uniform areas, creating an acoustic map of interstellar structure. This discovery proves that interstellar space isn't a void, but an active medium where plasma waves propagate across vast distances, potentially carrying information about distant stellar explosions, magnetic field reconnections, and other galactic events happening light-years away. The local interstellar cloud. Voyager 1 isn't just floating through empty space, it's actually swimming through what astronomers call the local interstellar cloud. Dr. Priscilla Frisch from the University of Chicago has spent decades studying this region, and Voyager's direct measurements have confirmed her theoretical models. This interstellar cloud extends roughly 30 light-years in all directions around our solar system, and contains about 0.3 atoms per cubic centimeter, which is incredibly sparse by Earth standards but still significantly denser than the cosmic void beyond. The cloud formed approximately 4 to 5 million years ago when multiple supernova explosions carved out a cavity in the interstellar medium. Voyager's instruments have detected the cloud's temperature at around 6,000 Kelvin, and confirmed it's moving relative to our solar system at 26 kilometers per second. As we drift through this cloud over the next 50,000 years, It'll gradually affect Earth's climate by modulating the cosmic ray flux that reaches our planet, potentially influencing cloud formation and atmospheric chemistry in subtle but measurable ways. The heliosphere's true shape. Everything we thought we knew about our solar system's protective bubble was, well, wrong. Voyager 1's journey has revealed that the heliosphere isn't the neat comet-shaped structure you might remember from textbooks. Dr. Merav Ofer from Boston University has been leading research using Voyager data, and her team discovered that our solar system's boundary is far more complex and turbulent than anyone predicted. The heliopause, that's the boundary between the solar wind and interstellar medium, varies dramatically in different directions. While Voyager 1 crossed this boundary at 121 astronomical units from the Sun, Voyager 2 encountered it at 119 AU, but in a completely different region with its own distinct characteristics. NASA's New Horizons spacecraft, still approaching this boundary, is providing even more data points that suggest the heliosphere might have a more irregular, possibly even fragmented structure. This discovery has profound implications for cosmic ray shielding and helps explain why the interstellar medium penetrates more deeply into our solar system than models predicted, creating these complex interaction zones where solar and interstellar forces are constantly battling for dominance. The density fluctuations. Interstellar space actually has weather, and Voyager 1 is our very first weather station beyond the solar system. Since 2013, the spacecraft's plasma wave instrument has detected at least 5 distinct density variations in the interstellar medium, each representing a different climate zone in deep space. Dr. Bill Kurth from the University of Iowa analyzed these fluctuations and found that interstellar plasma density can change by factors of 2 to 3 over relatively short distances. The most dramatic shift happened in 2014, when Voyager encountered a density spike that lasted several months, indicating passage through a compressed region possibly created by stellar winds from nearby stars. These variations aren't just random, they actually follow patterns that suggest interstellar space has structure on multiple scales. Some regions are compressed by shock waves from ancient supernovae, while others are rarefied cavities carved out by stellar winds. Voyager's measurements reveal that our local interstellar cloud has internal boundaries and substructures, making interstellar space far more dynamic and organized than the uniform medium astronomers once envisioned. The galactic coordinates. Every measurement Voyager 1 takes is helping scientists build humanity's first three-dimensional map of interstellar space. Dr. Nathan Schwadron from the University of New Hampshire leads the team creating these galactic coordinate systems, using Voyager's position as a fixed reference point about 15 billion miles from Earth. The spacecraft's current trajectory takes it toward the constellation Ophiuchus, where it will continue for thousands of years unless it's deflected by gravitational encounters. But Voyager isn't just traveling in a straight line, it's mapping magnetic field orientations, plasma densities, and cosmic ray gradients that, vary by galactic location. These measurements reveal that interstellar space has preferred directions and asymmetrical structures aligned with our galaxy's rotation. The magnetic field Voyager measures points toward the galactic center in some regions and away in others, suggesting complex field line geometries shaped by stellar formation and supernova events over millions of years. This galactic GPS system will eventually guide future interstellar missions, helping them navigate the invisible currents and radiation zones that Voyager is now charting for the first time. The temperature paradox. Interstellar space is simultaneously scorching hot and freezing cold, and Voyager 1 has measured both extremes. The interstellar medium itself reaches temperatures of 50,000 to 100,000 Kelvin, hot enough to vaporize any known material. Yet, Voyager's instruments register near absolute zero temperatures because the particle density is so low that there's virtually no heat transfer. Dr. Gary Zank from the University of Alabama explains this paradox. Individual plasma particles move at tremendous speeds, which means high temperature, but they're so spread out that the spacecraft actually experiences the cold of deep space. Voyager's cosmic ray subsystem has detected temperature variations in different regions of interstellar space, with some areas reaching 200,000 Kelvin, where shock waves from stellar explosions have compressed and heated the plasma. These temperature measurements reveal the energy budget of interstellar space, showing how supernova explosions, stellar winds, and galactic rotation, pump energy into the interstellar medium. Understanding these thermal processes is crucial for predicting how interstellar gas eventually collapses to form new stars and planetary systems. The communication miracle. Keeping Voyager 1 alive and transmitting from interstellar space represents honestly one of NASA's greatest technical achievements. Suzanne Dodd, Voyager project manager at JPL, oversees a mission using 1970s technology to communicate across interstellar distances. The spacecraft transmits with just 23 watts of power, less than a refrigerator light bulb. Yet NASA's Deep Space Network can still detect its whisper-faint signals after they travel for 22 hours at the speed of light. In late 2023, Voyager suffered a critical computer failure when cosmic radiation corrupted its flight data subsystem. Engineers led by Linda Spilker performed digital surgery across 15 billion miles, reprogramming 1970s computer code to bypass damaged memory sectors. The repair took months because every command required a 44-hour round trip for confirmation. By April 2024, they successfully restored communication with all 4 active science instruments. This remarkable resurrection really proves that American engineering from the space race era was built to last, giving us precious additional years of interstellar data from humanity's most distant explorer. The Golden Record's journey. Beyond its scientific mission, Voyager 1 carries humanity's greatest time capsule into eternity. The Golden Record, curated by Carl Sagan and Anne Druyan in 1977, contains sounds, music, and images representing Earth's diversity in 55 languages. Dr. Timothy Ferris, who produced the record, selected Bach, Beethoven, Chuck Berry, and traditional music from around the world. NASA engineers designed the record to survive billions of years in space, with instructions engraved in pure gold showing how to play it and how to locate Earth. The record includes greetings from President Jimmy Carter, UN Secretary General Kurt Waldheim, and children from all around the world. As Voyager travels toward the star Gliese 445, it'll make its closest stellar approach in 40,000 years, passing within 1.6 light-years of this red dwarf. Even after Earth's continents drift beyond recognition and human civilization evolves beyond imagination, the Golden Record will preserve our 1970s snapshot of humanity. Carl Sagan called it a bottle cast into the cosmic ocean, and now that bottle has reached the interstellar sea, carrying our message to whatever intelligence might someday find it drifting among the stars. Voyager 1 has shattered, well, just about every assumption about interstellar space, revealing a cosmic environment that's structured, active, and far more complex than we ever imagined. From magnetic field mysteries to plasma weather systems, this 1970s spacecraft continues revolutionizing our understanding of the galaxy itself. Voyager proves we live in a protected cosmic oasis, shielded from the harsh radiation of deep space. So, which discovery amazed you most? Drop your thoughts below. If you loved exploring these interstellar revelations, hit that like button, share with space enthusiasts, and subscribe to Future Facts for more incredible cosmic discoveries. What if the most important photograph in human history looked like a complete failure? We have the first clear images of 3I Atlas, the third interstellar object ever detected, and they show a blur, a smudge that refuses to focus. But hidden within that haze is a traveler older than Earth, an object moving at the very edge of physics. NASA doesn't want you to see how strange it is, but the truth is coming out. So, what secrets does this blur actually hold? Let's delve into it. Chasing motion. How do you photograph a ghost? Capturing 3I Atlas isn't like shooting an ordinary comet. It moves far too fast and shines too faintly for any normal exposure. By the time a telescope gathers even a few seconds of light, the object has already traveled thousands of kilometers. A single snapshot would show nothing but a faint comet-shaped guess. To overcome this, astronomers had to chase it. Advanced tracking software predicted the comet's path second by second, adjusting the telescope's mount in near real time. This technique forces the background stars to blur into long trails, but it holds 3I Atlas in a fixed position on the sensor. The still soft blur you see in the final image is not a lack of focus. It's the visual record of motion being perfectly cancelled out. A precise balance struck between the comet's incredible speed and the telescope's relentless pursuit. Even for veterans like astronomer Robert Warwick, who first spotted Oumuamua, an object at magnitude 17 moving this fast, is an extreme challenge. The team had to stack over 60 individual 300-second exposures just to get a coherent signal. This is less like photography, and more like assembling a ghost from whispers of light.
shape without surface.
So, what does this interstellar traveler actually look like? Here's where things get strange. In the image, 3I Atlas shows no surface. There is no crisp edge, no solid nucleus shining at its center. What we see instead is an outline that refuses to stay defined, a gray body that fades into itself. The elongation is unmistakable. It is not round, and it's not a random smear. It holds a deliberate structure, smooth at one end and uneven at the other. If this were a comet from our own solar system, we would expect a classic teardrop shape with a tail tapering behind it. But 3I Atlas shows a body that seems evenly stretched, almost like a cylinder, with no clear tail direction. This has puzzled every scientist studying it. The shape seems to hint at a rapid rotation, blurring its features together the way a long shutter turns moving water into a flat, silky surface. The team, using methods similar to those pioneered by Karen Meech for Oumuamua, detected a faint brightness variation suggesting a length-to-width ratio of approximately 3:1. This is far less extreme than Oumuamua's 10:1 ratio, but it makes the object's lack of a coma even more baffling.
The absence of color.
What color is a memory from another star system? When astronomers processed the raw data from the 3I Atlas image, they found something truly bizarre, an almost complete absence of color. Most comets, even faint ones, show a hint of tone, a greenish halo from cyanogen gas, or a yellowish tail from reflected sunlight. But 3I Atlas is a silent neutral gray. This lack of color tells us something profound. The object isn't actively releasing significant amounts of gas. If it were, those compounds would glow under the sun's radiation, painting the image with faint color. Instead, what we are seeing is pure reflection from a surface so dark it's estimated to have an albedo of just 0.02, meaning it reflects only 2% of the light that hits it, blacker than fresh asphalt. Planetary scientist Alan Fitzsimmons noted that while Oumuamua was reddish, this object's grayness suggests a different composition, perhaps richer in primordial carbons than silicates. Over millions of years drifting between the stars, its surface has been bombarded by cosmic rays, baking it into a material that absorbs almost everything. The color hasn't vanished, it has been cancelled out by eons of travel.
Edge of certainty.
How can we be sure this faint smudge is even real? In the raw data, 3I Atlas is barely a whisper above the background noise of space. When you zoom in close enough, the random static of the sky seems louder than the signal itself. But the difference between noise and a real object comes down to one thing: consistency. Real light behaves with intent. It repeats, it aligns, and it holds a pattern where chaos cannot. Across multiple long exposures, the faint streak of 3I Atlas appears in the exact same celestial coordinates. Its brightness curve remains stable despite atmospheric shifts and thermal noise in the camera. That repeatability is the only reason astronomers can call it real. The data achieved a 5 sigma confidence level, the absolute minimum threshold for an official discovery in physics. As astronomer Marco Micheli, who confirmed Oumuamua's strange acceleration, would argue a persistent signal, no matter how faint, must be treated as a real phenomenon. The final image isn't so much a photograph as it is a mathematical reconstruction, built one photon at a time until millions of calculations reduce the chaos into a fragile, undeniable geometry.
Refusing form.
What happens when a discovery refuses to be categorized? Once the image of 3I Atlas was assembled, it broke every analytical model it was put into. The algorithms designed to measure a comet's coma, nucleus and tail couldn't find a pattern. The numbers diverged, with each model insisting on a different shape. This usually means one of two things: either the target is unstable, or the physics behind it doesn't fit our templates. The faint elongation in the image doesn't align with the direction of the sun, suggesting it isn't venting material like a normal comet. It behaves like something halfway between the rocky, silent Oumuamua and the active comet 2I Borisov. It's too diffuse to be a solid asteroid, but too clean to be a gassy comet. That ambiguity makes classification nearly impossible. Harvard astronomer Avi Loeb has controversially suggested such anomalies could be signs of non-natural origins, and while most scientists disagree, 3I Atlas adds fuel to the fire by being so stubbornly unclassifiable. The object forces us to consider that our instruments were not built to understand what this truly is.
Mathematics of blur.
When an image can't explain itself, you have to trust the numbers. The frame of 3I Atlas is too ambiguous for traditional analysis, so scientists turned to pure mathematics to reveal what the light could not. By plotting its position with micro-arcsecond precision across consecutive nights, they calculated its velocity at roughly 12 kilometers per second relative to the Sun. This confirms a hyperbolic eccentricity of 1.1, the mathematical proof that it's just passing through, moving too fast for our Sun's gravity to ever pull it back. Next, brightness simulations show that if the nucleus is elongated, a slow 11.2-hour tumble could perfectly recreate the uneven brightness we see. Even the blur itself becomes a measurable variable. As orbital dynamicist Davide Farnokia explains, by deconvolving the image, you can reverse the distortions and find that residual motion smear accounts for about 30% of the elongation, with the rest being the object's actual shape. The image shows uncertainty, but the equations show precisely why it has to look that way.
Distortion or discovery.
Is this a groundbreaking discovery or just a glitch in the machine? With an object this faint, that's honestly the most important question. At these low light levels, distortion is just part of the data. Cosmic rays can create false flares and tiny errors in the telescope's tracking. Even just a fraction of a pixel can add up over dozens of frames, creating a false elongation that might be mistaken for structure. So, is the cylinder shape of 3I Atlas real? Here's the bottom line. When independent teams processed the images using entirely different software, the same general shape still remained. The angle, the brightness gradient, and the faint tapering all persisted. If distortion were the only cause, its signature would change between systems. Instead, the shape repeated itself, stubbornly and quietly, almost as if the comet's true geometry was asserting itself through the noise. Spectroscopist Michelle Bannister noted that even a slight reddening on one side of the blur is consistent across multiple datasets, which hints at a real physical or compositional feature. It exists right on the threshold where every feature we see is a battle between signal and noise, between a real object and, well, the struggle to see it.
Escaping definition.
At some point, the discussion around 3I Atlas stopped being about what it looked like and started being about what it refused to be. It is not a traditional comet, it has no coma or tail, it is not an asteroid, its light curve varies too smoothly to come from a simple rocky surface. The image presents something in between, a blur that resists every attempt at interpretation. Its trajectory confirms an interstellar origin, and paradoxically, that certainty of escape is the only thing about it that feels familiar. The data now paints a picture of pure contradiction, a stable brightness curve suggesting a single body, yet an asymmetry that hints at fragments orbiting a shared center. This object is defined by the fact that no existing model can describe it cleanly. As astronomer Matthew Knight puts it, sometimes an object's most important feature is its refusal to conform to our expectations. This forces us to confront the idea that seeing is not the same as knowing and our categories are only conveniences, not cosmic truths.
Between categories.
Where does this visitor fit in with the others? Our first interstellar guest, Oumuamua, was sharp, fast, and completely inert. The second, 2I Borisov, discovered by Gennady Borisov, was almost too familiar, behaving like a classic comet from our own backyard. 3I Atlas sits perfectly between them, as if bridging a gap. It's neither solid rock nor active comet, neither silent nor loud. It behaves like a memory of both. Its faint cylinder of light is the signature of something that exists just beyond the boundaries of our resolution and our taxonomy. This suggests that the objects drifting in interstellar space are far more diverse than we ever imagined. Perhaps our solar system, with its neat categories of asteroids and comets, is the real exception. David Jewett, a key researcher of the outer solar system, emphasizes that with only 3 data points, every new object dramatically reshapes our models of what's out there. 3I Atlas isn't just a third data point, it's the one that shows us the two extremes were not flukes, but part of a vast and largely unknown spectrum of cosmic objects.
Measured by blur.
When the light from 3I Atlas finally fades from our sensors, this photograph will be all that remains, a faint smear in an archive. In most sciences, such an image would be dismissed for its lack of detail. In astronomy, it becomes the most honest kind of evidence. A blur is what happens when the scale of the universe meets the limits of our focus. Everything measurable about this object exists inside that single unresolved streak. its speed, its path, its rotation, its distance. From this one imperfect shape, entire models of its journey emerge. We don't know what it looks like, but we know what it's doing. Soon, it will leave our system and recede into the same dark it came from, never to be seen again. This blur is not the beginning of a study, it is the end of accessibility. Paul Chodas of NASA's Kinios has stated that such flybys are fleeting gifts from the galaxy. It's the one clear record of a body from another star crossing through our home, measured by its blur. This interstellar traveler was never truly seen, only measured. Its secrets remain locked in a blurry image that asks more questions than it answers. Is it a fragment from a destroyed world, a failed comet, or something else entirely? The debate is only just beginning, and the strange, cylindrical ghost will haunt astronomy for decades to come. Its existence proves that the universe is not only stranger than we imagine, it is stranger than we can imagine. What do you think this object really is? Let us know your thoughts in the comments down below. Don't forget to like, subscribe, and hit the bell icon to stay up to date with all things 3I Atlas. Thanks for watching Future Fact. What if the most profound discovery in human history was made, and then deliberately buried? We're not talking about rumors or grainy photos here. We're talking about 24 gigabytes of classified NASA data on an interstellar visitor that, honestly, just defied the laws of physics. Data leaked by a ghost-like hacker group revealing a 26-kilometer-wide object that wasn't just passing through our solar system, but get this, actively navigating it. This is the story of 3I Atlas, what NASA allegedly found and why they never wanted you to see it. Let's delve into the data. Event Horizon cyber attack. How does a secret stay buried in the digital age? Well, sometimes it just doesn't. In the dead of night on September 2nd, 2025, a hacker collective calling themselves Event Horizon executed a flawless cyber attack on NASA. They didn't just knock on the door, they dismantled it. By exploiting a zero-day vulnerability in an outdated mission planning module, they bypassed layers of federal firewalls. Security logs, which were later leaked themselves, show a terrifying timeline. At 3:14 a.m. Eastern, initial access was gained. By 3:19, they had escalated their privileges to the highest level. At 3:23, the exfiltration began. In less than 7 minutes, 24 gigabytes of compressed files were siphoned from a secure server containing mission telemetry, internal communications, and top-secret analysis on Object 3Y Atlas. By 3:30, they were gone. The attackers left no signature, no digital fingerprints, only a silent void in the server logs where critical audit trails should have been. The specific target was a data archive tied to the Deep Space Network, containing the most sensitive raw telemetry. NASA's internal cyber forensics team was left with nothing but a clean exit, a ghost in the machine that had walked out with the crown jewels. The manifesto and distribution. A data breach is one thing, but a declaration of war on secrecy is another. Within hours of the hack, a manifesto from Event Horizon appeared on encrypted forums. Their message wasn't a boast, it was a justification. They claimed the breach was a direct response to what they termed unlawful cosmic secrecy, arguing that discoveries of this magnitude belong to humanity, not to a select few government agencies. The manifesto warned that the stolen files contained information so sensitive even senior directors at NASA were allegedly unaware of its full scope. Their language was direct: the world deserves to know what its own scientists have found. To prove their point, they began a strategic distribution campaign. Blurred screenshots and heavily redacted memos were sent to journalists and channels known for covering classified science. They specifically avoided mainstream outlets, opting for platforms that would analyze the data without an institutional filter. This drip feed of information created a groundswell of speculation that legacy media couldn't ignore, forcing the conversation into the open on Event Horizon's terms. Authenticating the documents. How can we be sure these leaks are real? The proof is in the details. The screenshots that flooded encrypted channels are layered with evidence of their origin. Documents are stamped confidential in bold block letters. Metadata tags show a 0314 UTC timestamp, matching the breach window from NASA's own security audit. A mission patch appears in the corner, a stylized comet streaking past a NASA vector, flanked by the code 3I Atlas int. One partially blurred memo lists the object's trajectory with terrifying numbers, hyperbolic v infinity of 26.1 kilometers per second, and an eccentricity, or E, of 6.2, these figures confirm an interstellar origin at a speed that, honestly, just defies simple explanation. Another screenshot shows a status log from the intercept team. Most text is blacked out except for a single phrase. Plume anomaly flagged at T plus 11.3 seconds. The documents include FITS file headers for raw imaging data and internal routing codes for JPL's document management system. These are the kinds of mundane technical details that are nearly impossible to fake convincingly. Discovery of 3I Atlas. Before the leak, there was the discovery that started it all. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, or ATLAS survey in Hawaii, logged a new object tearing into the solar system at 130,000 miles per hour. Astronomers flagged it immediately. This was no ordinary comet. The object, soon labeled 3Y Atlas, measured an estimated 26 kilometers across, roughly the size of Manhattan, moving faster than any object ever observed inside the orbit of Jupiter. Veteran survey scientist Dr. Lina Takahashi, a fictional name from the leaked files, was quoted in a log. The track was so steep, the software flagged it as an error. Within hours, observatories from Chile to Arizona confirmed the numbers. The object's incoming speed of over 58 kilometers per second defied the sun's gravitational grip. Its trajectory pointed back toward the constellation Lyra, far from the ecliptic plane where most solar system debris resides. To put its size in perspective, the asteroid that killed the dinosaurs was only about 10 kilometers wide. This was over twice that, and it wasn't from around here. Impossible physics and trajectory. Here is where the data gets terrifying. The trajectory of 3I Atlas was not just interstellar, it was unnatural. Calculations from the Minor Planet Center confirmed by JPL revealed an orbital eccentricity of over 6. For context, most comets from our own Oort cloud barely reach an eccentricity of 1.0. Our first interstellar visitor, Oumuamua, had an eccentricity of 1.2. A value of 6.2 means the object was moving on an almost perfectly straight line at a velocity that gravity could barely alter. But the most damning piece of evidence detailed in the leaked mission logs was a sudden unexplained sideways acceleration on July 18, 2025. It was a course correction. The object wasn't just flying, it was steering. The maneuver required a change in velocity, or delta V, that would have required gigatons of force to achieve on an object of this mass. All natural explanations, outgassing, solar radiation pressure, even a gravitational assist from an unknown planet, were systematically modeled and ruled out by JPL's top analysts. The physics simply didn't work unless the push came from within. Surface anomalies, the armor problem. What does a 26-kilometer object from another star system look like? The first leaked images from the intercept mission were paradigm-shattering. 3I Atlas's surface resembled no comet on file. Imaging analysts flagged a pattern of smooth, almost metallic-looking plating, broken by lines that ran too straight to be natural fractures. One analyst, quoted in a redacted chat log, called it the radiator problem, referring to a gridwork of raised ridges spaced like the cooling fins on spacecraft. These ribs cast long, uniform shadows, and their regularity caused the anomaly detection software to flag the pattern as artificial. Comparisons to known comets like Halley or 67 P. Churyumov-Gerasimenko fell apart. Their surfaces are jagged and chaotic. 3I Atlas, in contrast, had long stretches that reflected sunlight like polished alloy. Further spectral analysis of this reflected light showed an albedo inconsistent with any known meteoritic iron, lacking the usual chondritic features. It was too smooth, too reflective, and far too structured. Thermal signatures and heat pulses. This is where the data points directly to active technology. Martin Cordner's team at Goddard Space Flight Center, a name appearing in the leak, got a full infrared spectrum of 3I Atlas. The data was so sensitive it was sealed within hours under a restricted embargo. The logs show the Webb telescope's infrared array recorded heat vents pulsing with the regularity of a clock every 90 seconds. Heat would pool along the radiator seams and then burst outward in tight directed jets, not the broad, chaotic outgassing of a comet. The mission logs label this a directive motion event, a term usually reserved for spacecraft thrusters. More disturbing, trajectory analysts correlated these thermal pulses with the object's subtle course corrections. Each 90-second heat pulse matched a tiny, precise adjustment needed to maintain its hyperbolic escape route. The focused nature of these thermal events implies the existence of engineered nozzles or vents, as a natural body's heat would dissipate uniformly across its surface according to the laws of thermodynamics. This was controlled, focused, and undeniably artificial. Chemical composition mysteries. The mystery only deepens when you look at what 3I Atlas was made of. Martin Cordner's team at Goddard was the first to get a full spectrum after the intercept, and the results were an instant red flag. The early spectra lit up with incredibly sharp, bright lines of nickel. In cosmic bodies, nickel almost always rides shotgun with iron. Yet in every single frame of data from 3I Atlas, iron was almost completely absent. Its signature spectral lines were missing. This isn't just rare. In the entire catalog of known comets and asteroids, it's unheard of. The natural formation processes that create asteroids from protoplanetary disks simply don't separate these two elements with such purity. Leaked notes suggest the isotopic ratio of the nickel was also wrong, indicating it wasn't formed in a typical supernova. The purity level was estimated to be over 99.8%, a level that on Earth requires an advanced electrochemical process known as the Mond process. Radio echoes and communication patterns. Did we ever try to listen? According to the leaked files, yes. And what we heard was terrifying. While public-facing projects might report silence, the classified logs from the Deep Space Network told a different story. Radio astronomers reviewing the intercept mission's raw data flagged a pattern that shouldn't have been there, faint, repeating echoes bouncing back from the object at regular intervals. These were not natural radio bursts or cosmic static. They were precise, clipped signals echoing at intervals that mapped almost perfectly to the 90-second timing of the object's thermal pulses. A veteran telemetry specialist named Marissa Singh, in a chat log later leaked by Event Horizon, wrote, "It's like someone is pinging the probe and it's answering. The pattern is too tight for random noise." The return signal wasn't a simple reflection. It was modulated, carrying a complex phase shift. It was, for all intents and purposes, a reply. This suggested the object was not just passive, but an active system processing and responding to incoming stimuli. Expert analysis and propulsion theory. You can't discuss these anomalies without bringing in a voice of scientific courage like Avi Loeb. The Harvard astrophysicist, who famously staked his reputation on Oumuamua being alien technology, wasted no time weighing in on the 3I Atlas files. He argued the intercepted telemetry read like a blueprint for an advanced propulsion system. Each 90-second heat pulse and corresponding course correction was perfectly consistent with a massive ion drive or a similar engine. In Loeb's words, if you wanted to navigate through a solar system while managing heat and energy, you would use timed, directional thrust. That is what the data shows. But the most jarring evidence was a fragment recovered by the interceptor's dust collector. A leaked lab memo described a fleck of material with a lattice of silicon and doped phosphorus, arranged in layers spaced at micron intervals. The structure was noted as being radiation-hardened to a degree far beyond current human capability, suggesting it was built for long-duration travel through the harsh interstellar medium. This wasn't just a circuit, it was an artifact from a civilization far beyond our own. So, what does this all mean? We have a fictional but detailed account of an interstellar object, 3I Atlas, discovered in 2025, and we have a leaked cache of alleged NASA documents that point to a disturbing conclusion, that the object was a piece of technology. Metallic armor, rhythmic heat pulses that act as thrusters, refined nickel, and structured radio echoes all point to an artificial origin. The most shocking piece of evidence, a microscopic fragment that resembles a computer chip, pushes this story from science fiction into something far more unsettling. While the leak itself is part of this narrative, it forces us to ask a terrifying question. What if our first definitive contact isn't a message but a 26-kilometer machine flying silently past our window? The truth is still out there. Don't forget to like, subscribe, and hit the bell icon for more deep dives into the secrets of science and technology. Thanks for watching Future Facts.